Good.
Okay, excellent. So my name is Phil Hasnip, and I'm based at the University of York, as Filippo said, and it's a pleasure to talk to you today. I'm currently at a digital research infrastructure retreat, so I'm sorry I couldn't join you this morning, and I'll probably be disappearing at the 2:30 break. I'm sorry about that. But I'd like to tell you a little bit about our journey using the first principles code CASTEP and trying to use GPUs. And a lot of the infrastructure that CASTEP does, a lot of the way we work is very similar to VASP. So Stefan and I talked a little bit, we've arranged that I'm going to do a slightly overview of plane wave DFT, as we'll see, and then I think probably Stefan will present some more details, computational details, but I'm quite sure either of us will be very happy to answer questions. So there'll be plenty of time for that. So just to start with, what are we trying to accomplish with something like CASTEP? Well, first of all, let's start with what it does and what the scientific aim is. What we're trying to do is take a material that we've never seen before, perhaps, it might even never have been made before, and predict what it does from what we call first principles, which really is code for quantum mechanics. So something that has as few approximations and parameters as possible. And most of the physical and chemical properties we're interested in are governed by the electrons. So this comes down to how do you model electrons? And we model this with density functional theory. I'm going to say basically no more about that, but that's the method that we use. And the key idea is that the material's behavior should just emerge from the simulation. It's not an input, it's just an output of the simulation. Now that's the sort of science pitch and the sort of strategy, but what does it really look like? Well, in terms of CASTEP itself, we use the method generally known as the plane wave pseudo-potential method. So we write our quantum mechanical wave functions in plane waves in a Fourier basis. It's somewhere between 500,000 and 750,000 lines of code in modern Fortran 2003, a little bit of 2008. And it's parallelized on CPUs with hybrid MPI and OpenMP. The MPI has always been there, and the OpenMP is, I think of it as new, but it's probably, it's over a decade old now, but it's the newer one. And just a little bit about the distribution. So it's free for academic use. In fact, it's free for non-commercial use. We have a cost-free license, and commercial use is marketed by a BioVia part of Dassault. But its core development is in academia, and it's free for academic use. And in fact, these days, it's all in the UK. So it's York, Warwick, Oxford, Durham, and Cambridge who do the development. Okay. So when this has been working quite happily on a wide range of machines across the world, and we have many users. But when it comes to GPUs, the first thing is, of course, what's a GPU? But how do you exploit that? And I've picked 4 technologies that you might look at: OpenCL, CUDA, OpenMP, and OpenACC. OpenCL, if you've ever used it, is really akin to OpenGL, the graphics library, and it is very portable, but it is relatively low level. You have to do a lot yourself. The sort of caricature is that you make your program look like a shader, and then you're fine. It's not as bad as that, but you have to care a lot about the minutiae of everything. Almost at the opposite end, we have CUDA. CUDA, of course, is NVIDIA only, which is fine for the MMM hub system, but you might want to work on a wider platform. And it's only supported by a certain number of compilers. And in fact, from a Fortran perspective, it's pretty much only the NVIDIA compiler that will do proper CUDA. There's OpenMP, which is being pushed by certain sectors, which we use for the CPU parallelism and has gained some accelerator offload features. And then there's OpenACC, which is in the spirit of OpenMP, but has a much more mature set of accelerator directives and some extremely helpful quality of life enhancements. And you may have guessed from my description of those, we've chosen OpenACC. We've chosen it because it is a technology that allows us to keep our CPU code base largely, add directives to it, as we could do with OpenMP, and target specific data and specific work to offload to the GPU. It gives you the control about what goes on the GPU and what goes on the host without having to specify exactly how things are executed on the GPU. So for us, it's a nice level of abstraction, and it also is a nice portable and sustainable architecture for not having a GPU branch, but having a single code base that can serve CPUs and GPUs. We are a small development team. When I listed our universities in the previous slide, it's basically one academic per university. So we can't afford to fork our code base. We need to keep it maintainable. There is the danger that we sacrifice some performance in doing this. Our early experience is that, yes, if you did, for example, CUDA, you could get a little bit more performance out of it, but it did take a bit more effort. And sometimes when a new accelerator technology came along, I don't necessarily mean not NVIDIA, I mean even going from Pascal to Volta, for example, some of the CUDA worked, but needed to be slightly rewritten, and certain details of the hardware you needed to take into account. Whereas with the OpenACC, you could mostly recompile and gain the advantages of the new architecture. So from a staff cost, an investment in code, OpenACC was quite a strong contender. Now, in a minute, I'll show you the kind of thing that we've done. But before I do that, I just wanted probably a recap to many of this audience, just to say, when I say DFT, what does it really do? Where is the time actually spent? So really, when we say DFT, we mean there's an eigenvalue-like equation. So here I've written, you can think of it as a matrix H on a vector we call psi, and that is E psi. E is a scalar here, the energy on the same wave function. So it's an eigenvalue equation. It's a slightly awkward one because it turns out that my matrix H depends on psi, so I have to solve this iteratively, but it is at its root a eigenvalue problem. Now, we are exploiting the fact that materials are periodic in their structure, and the wave function has some of the qualities of that periodicity, and we're using a Fourier basis, normally called a plane wave basis, to represent wave functions. And in one sense, that's not relevant. But what it means is the plane wave basis is very mathematically simple. It's very computationally simple, but it is not compact. It's at the opposite end of the scale. You have local basis sets, which perhaps you might hear about in the CP2K talk, but where you have just a few basis sets per electron. We are not there. A simulation of 1,000 electrons might easily have 1,000,000 plane waves. So when I say this is an eigenvalue problem, this is an eigenvalue problem that might be millions by millions in the matrix, but I only actually want hundreds or thousands of states. So I want the states with the lowest energy. And what that means is I don't actually construct this Hamiltonian matrix. It would be huge. I use iterative methods where all you have to do is apply this matrix. And the way we do that without constructing it is we break it down into 4 main components. We have the kinetic energy part, which is very compactly represented in the plane wave basis. We have a sort of potential term, which is not compactly represented in the plane wave basis, but is very compact in real space, what's computational people sometimes call direct space, but the space that we live in, normal space. And then there are 2 other terms. One of them comes from our use of pseudopotentials, and it's called the non-local potential. That's what I call VNL. And another is from a very specific class of calculation where the quantum effects of the electrons are handled with a very non-local interaction. And this is relevant if you're a chemist, you'll know this from things like Hartree-Fock, maybe B3-Lip. If you're a physicist, you might know this from screened exchange or from the HSE functionals. So there's a lot of hybrid functionals that involve this. I'm not going to talk about the physics at all, but it's important for the computational workload. These two operations are important. They take a long time. The VNL, VNLXC, each take a long time. So it's for big systems particularly. So that's what we're going to look at primarily when we think our story of using the GPU. So computationally, VNL is mathematically a low rank matrix update, which means, in other words, it looks like a lot of rectangular matrices, and you're sort of doing a lot of dot products between your wave function and these matrices. And that's all done in linear algebra. So it's in the CPU, it's done entirely in the maths library. We use the basic linear algebra subroutines, the BLAS interface, which is pretty standard. So when we come to look at, well, how can we do this on a GPU? For a big system where this dominates, it's relatively straightforward. You use OpenACC directives to tell the compiler where you want to move what data to the GPU. Your BLAS call, well, there isn't any OpenACC to do that, and you might need to do CUDA, but thankfully, NVIDIA have worked on that. There is a QBLAS, which is literally their optimized BLAS that runs on the card, on the GPU. So at least at a high level, your OpenACC does the data transfer. QBLAS does the same BLAS operation you were going to do on the CPU, but now on the GPU, and then use OpenACC to drag the data back. And it's as simple as that. As long as you don't have any bugs, it's as simple as that. And actually, I'm not going to talk really about this, but the local potential is quite straightforward, but involves a Fourier transform. And similarly, there's QFFT. As long as you've moved the data to the right place, QFFT can do the Fourier transforms there. So if we look at that doesn't dominate for large systems. For smaller systems, it can be important. The number of FFTs that you have to do depends on the number of electrons you have, the number of bands of your material that you're interested in, and the number of sampling points, NK, which are the points in the Brillouin zone. If you're a materials person, you'll know what that is. Now, the bit that gets a bit complicated here is I want to do a 3D Fourier transform. If I can call a single 3D Fourier transform, maybe with FFTW, the 3D one, this is easy. I transfer the data to the card and I do the 3D Fourier transform. But CASTEP is often used in large parallel systems where we might have distributed the Fourier data. And so now my FFT is a parallel FFT, and there's a lot of communication involved in dragging data to where you actually need it. The way we do that is we decompose the 3D FFTs into lots of different 1D FFTs. And then we do some explicit MPI communication so that you figure out what everybody else has transformed and you could do your next transforms. So you can think of it as you do 1D FFTs in a particular direction, maybe your X direction. And then everybody talks to each other and rearranges the data. And then everybody does FFTs in the Y direction. And then everybody talks together. And then you do FFTs in the Z direction. And this is a problem on GPUs because you are taking data onto the GPU, which takes some time. You're doing only a 1D FFT, which doesn't have a huge amount of compute. And then probably you're dragging it off the GPU onto the CPU to do some MPI comms. And then you need to do FFTs in the different directions. You've got to get all back on the card again. So you can do it technically. Programming this is easy. Do OpenACC to transfer the data to the GPU. You do QFFT for the operation. That's all fine. But getting performance can be quite tricky. Let's assume for now that's a solved problem. let's parallelize over the bands and K points so we don't have to worry about these parallel FFTs. What do we get? So this is some results for a particular benchmark. It's not really important, but it's for those who are interested, it's iron vanadium aluminide, a thermoelectric material, on the Bede machine, which is not the same as the MOM hub. It's an IBM Power 9 with V100s, so the Volta architecture. And this is the time per iteration for this benchmark on the CPU, just the CPU. And then what we do is we use the V100s in addition to the CPU. So we haven't migrated the whole of CASTEP onto the GPU, we've just offloaded the local potential and the non-local potential that I just spoke about. And what you see is that right across the scaling data here, as we go across the nodes, the GPU solution is faster. The scale is hard to say exactly how fast is just from this graph. We'll come to that in a minute, and what other implications for scaling. But you can immediately see there is no point at which the GPU is a bad idea. So my first take-home message to you is you can quite easily get to the state where a system that has GPUs, it's worth using the GPUs. The challenge will come, well, let me just move on to, let's see what the speed up is. So if I take the ratio of those two, first of all, let's look at the parallel scaling. And the parallel scaling is pretty good across the GPUs. And this is a multi-node calculation. You can see we're going up to filling most of 6 nodes here. We're getting reasonable scaling. It deviates from linearity because of the communication cost, but it's really not bad. And actually, I haven't shown you the CPU scaling because it's identical. The GPUs don't change that. Speed up. So literally the ratio between the GPU and the CPU time is pretty consistently a factor of 2. And this is a reasonably small benchmark. It's not huge. So the bigger the system, the bigger the speed up, because we're doing more effort in the non-local potential. And that scales cubically with your simulation size and goes really nicely on the GPU. So this is sort of solved at this level. And what speed up you get is a matter of, well, I can artificially get a better speed up by running a bigger system. But I want to be honest here, this is a relatively small system and you can genuinely get a factor of 2. For doing something reasonably straightforward code-wise, the challenges come when you move beyond, when you go to parallel FFT. Okay, just in the last couple of minutes then, and feel free to ask questions about any of this, there is a significant technical drive, especially in the device materials community, to use this last term, the non-local exchange correlation, because it gets various electronic properties much more accurately that are required for transport, for example. And the catch is if you do this exactly correctly, formally correctly, it requires Fourier transforms and a lot of them. The local potential requires NB, NK Fourier transforms. This method requires NB squared, NK squared Fourier transforms. And the result is that applying this fourth term is usually bound completely by the FFTs. It can be 98% of the runtime just in this term. The rest of the Hamiltonian is almost free. So if you're doing 3D FFTs, this can be offloaded and accelerated really, really nicely. But we have an ongoing challenge of 1D FFTs. The 3D Fourier transforms now become the bottleneck. On the GPU, they go really very quickly. In fact, it becomes a question of how quickly can you feed the GPU. And when you have this NLXC, we did this for the same calculation, but I haven't done the multi-node one. So this is one node of Bede. Actually, it was a cent in Oak Ridge, but it's a very similar architecture. This is the speed up relative to the CPU. This is using 42 cores of a Power 9. That's the left-hand one labeled CPU. And when we did what I've just told you about, that kind of exercise, we got the middle one, our initial GPU. We got a speed up of 8, which we were happy with. But when we looked at it, we were struggling to feed the GPU. The GPU was idle for quite a long time. So our easy win that I told you about a minute ago, where you decorate it with OpenACC and then you offload to QFT, got us a factor of 8, which is good. Most of us would be very happy with that. But the memory bandwidth factor is something like 15.5. And we looked at the profiling, we saw the GPUs idle for a lot. So what we ended up doing is refactoring the code, which was more effort, to bundle up FFTs to what they call batched the FFTs, and to make the bits to do the work, the kernels, to fuse them together. So instead of having this region on the GPU and this region on the GPU, to make a bigger region on the GPU. And that meant that the GPU could be utilized almost 100%. And we get a speed up of, depending on your benchmark, 14.5 to 17, which is pretty much the ratio of the memory bandwidth from the GPU to the CPU. So if you are bottlenecked ultimately by how fast can you feed the thing, a factor of about 15 is perfect. You can't beat that. Okay, I think I'm out of time. So let me say, whenever I've said I or we, what I really mean is Matt Smith, PhD students in Cambridge, now at Barcelona Supercomputing Centre. Ian Tamaris, an HPC specialist at Cambridge. Ed Higgins, our research software engineer at York. A bunch of NVIDIA guys who've advised us and helped us, and in the case of one of the dev techs, actually really helped us in some of the code. Hackathon teams from Bede, Sheffield and Oak Ridge, and it's all been funded directly or indirectly by EPSRC. And I'll just leave you with the bits I've obviously not talked about, which is the challenges. This is if you if you use CASTEP, I've told you probably anything you need to know about it. But if you don't use CASTEP, you want to learn the lessons. These are the bits that we're facing now or recently faced. These are the challenges. How you can use the GPU and maintain a sensible, portable, and sustainable code base, and how we can do the tricky stuff with massive parallelism over CPUs and GPUs and get the best of the whole system. And I will leave it there. Thank you very much for your attention.
Thank you, Phil. Does anyone any question for Phil about CASTEP, the performance, their journey? I have a short question, just to break the ice eventually. How long it took and how many people?
So to get to this point, it's been a long journey. There were a couple of false starts, I think, early on. For us, the real breakthrough was developing a relationship with NVIDIA, and in a way that and both of us understood what the other was interested in and was able to deliver. And I think in terms of the main work, it's been probably 4 years of mostly just one person working on it, but not always the same person. And the people I've acknowledged here, that's the sum total of everybody who's worked on it. So Matt, Ian and Ed, in fact, less Ed, really Matt, Ian, and to a lesser extent me, that's the team. 3 people to port a 2/3 of a million lines of code in modern Fortran GPUs. And we haven't finished, there's a lot more to do. But hopefully you've seen that actually you can get some very useful speedups. And you can really exploit a GPU machine. The bit that is tricky or trickier is it worth buying a GPU machine versus is it worth getting a more CPU nodes? And it's a bit break even at the moment. We've got to the point where it probably doesn't matter for CASTEP. But we'd like to go beyond that and make GPUs just unequivocally a good thing.
Okay. Thank you very much.